This short video will show how to create a bidirectional driver within StarDraw Control. So the device that we're going to try and get feedback from is a Tascam DV-D01U DVD player. And we can see from the command structure for an RS-232 command to this device, we'll see that every packet begins with a 2 and every packet ends with a 3. And then everything in the middle here is actually ASCII. So it starts with a preamble of a greater than, then a PLY, because this is an example of the play command, followed by a lowercase c, because that's the command, and then the parameter codes, FWD in this particular case, and then followed by spaces, because every packet is 17 bytes in total, followed by the checksum. So let's first of all see if we can go and see what the code is like to go and send out this command. So within StarDraw Control, we'll just go and add a new product, and we'll say it's a Tascam, and it's a DV-D01U DVD player. Okay, and we're going to add a port. We'll say it's the serial port, and it's RS-232 input. And if we click on edit, we can then go into the script editor to go and see the script used to control this device. There's a whole bunch of comments here which we can just delete, and that is basically what the driver is. That doesn't do anything. So now we're trying to send out that play command. So we'll have a controllable function, call it play, and all it will do is go and write out a string. Now if we come back to the PDF, it wants a 2, which we can do here by specifying the hex 02, and then greater PLY, and then a CFWD, and then 1, 2, 3, 4, 5 spaces, 1, 2, 3, 4, 5 spaces, then a 17, and then the 3. Great, and that's all you would do to go and get the DVD player to issue a play. Now, how do we get feedback from this device? Well, if we have a look at status information request packet, what you actually issue is, here's one for like mod that can go and return the transport status, and we'll see how that works. Now the mod request is very similar in packet structure, but this time it's got MOD in there and a whole bunch of spaces. So let's go and add another function here. Request status, and what we'll do is write out again x02 greater than, and then it's MOD, and then it's MOD, and then lowercase space, and then it's 1, 2, 3, 4, 5, 6, 7, 8 spaces, 1, 2, 3, 4, 5, 6, 7, 8, followed by the checksum, which is 8, 1, and then finishing off with 0, 3. Great, so that's requested the status, but how do we get the response back? Because we cannot do a write here, because that write, there is no, first of all, there is no write, sorry, there is no read, because it will actually block until it gets some status back. We don't want to do that because being a bidirectional multi-threaded system, that device might actually take some time to respond, because when you do that write, it won't actually send it out straight away. It'll be scheduled to be written out on another thread, and then sometime later it gets sent out, and then sometime later the device will receive it, then sometime later the device will respond, and sometime later we'll actually get that response back. So how do we actually get that data back when it does come back? The answer is we have a protected overridable function called 2 R's in override, called onByteIn, and it takes one parameter, which is some data. Now the first thing you should do is always go and call the base function onByteIn, and do that. And that will just go and call the onByteIn implementation inside the serial import instance. So when we've got that byte in, what do we do with that? Well, the answer is that we need to go and build up a packet internally. So we're going to define a private system.collections.ArrayList, which is just going to build up an array of these bytes as they come in. And we're just going to call this list, and we'll say it's a new system.collections.ArrayList. Okay, so we've got the list that we're going to build up. And quite simply, if the data that comes in is equal to a 2, then that indicates the start of the packet. So what we'll do is we'll do a list.clear and clear anything that was in there before. Otherwise, if the data is 0x03, it's the end of the packet, then we want to go and call a function called processPacket, which we'll implement in a second. Otherwise, it's just a regular byte, so we'll just do a list.add of data. Great, so that deals with the byte in and the processing of packets, or the processing of bytes to build them up in a packet. So what we'll do now is we'll go and implement that function processPacket. Now, just to check everything is working fine, what I'll do is log out inside processPacket. Now, logger.debug is a very useful method for seeing what's going on in the system in the background on different threads, because this will be logged out on the debug window, and we can see the data that's coming in. So we'll just check that that is all working fine. Now, I don't actually have one of these devices physically connected to my machine, but what I do have is, if I go and drag this out onto here now, I have a global cache, just a GC106, and I'm going to fool it into thinking that that's actually connected on the serial port. So I can see any data coming in. What I've actually got connected on the serial port is my COM1 port. So I've actually got a couple of files here, which are the actual command parameters. If I type in play.bin, we'll actually see there is the actual bytes. We can actually dump this out and see the command that's coming there. And this is the response that will come back for the play. So this is this actual response. Right? And I've actually said that this is a play, which is hex 3A in here, and we should see that say colon right here. So here's the bytes. Now I can actually copy play.bin to COM2. First of all, we'll make sure of what COM2 is, and it's set to 9600, which is the right baud rate, and I've already configured the global cache to be 9600, so I can say copy /b play.bin to COM2, and /b just because it's binary. Okay, so I won't hit enter on that just yet, and I'll just hit run on here. This will now compile, run the executable, switch into debug mode, and there is the initialization. I'm actually talking to the global cache there. So now if I come into here and copy, we should see it come through onto here. I'm sure it does. There is the bytes that have come in, and we've caught that there is the end byte, and we're inside the process packet. Great, so now we've got packet. Let's go and process it. So to edit that driver, we can edit it in place, and we just go and click on edit and edit, and we're inside the process packet. So we need to do things like First of all, go and get the array of bytes from that list, and we can do that by a nice little function where we're going to convert this to a byte array and do a list.toArray of type of byte. So that's just a little bit of magic to go and convert the array list into a byte array. And then because we know it's a string, it's going to be useful for us to get a stringified version of this, because we know it hasn't got the first byte, because all it did was a clear that, and we know it hasn't got the end byte because it just did the add there. So all that's going to be in this packet is everything from here up to here. Okay, so let's go and convert it to a string. And this is the actual real packet. We're going to system.text.encoding.ascii.getString, and we're just going to pass in that array. Okay, and again, just to check that that is correct, we're actually going to say packet equals packet. So we should see that coming in there. Great. Now what we want to do is absolutely make sure that this packet is correct and in the right format. So what we're going to do is do some checksum calculations. So we're going to check this BF here. Now, according to the RS-232 specification, the actual checksum here is between this byte and this byte. It doesn't actually include the checksum itself. So we've got our packet goes from here to here. We just need to knock off those 2 bytes and add all these up and check that the checksum is correct. So let's just go and do that here now. So we'll say byte checksum equals 0, because we're going to initialize it to 0. And what we'll do is we'll just go in a little for loop going from I equals 0, I less than array.length -2, because we don't want those 2 last ones that are the actual checksum. I++, and we'll say checksum plus equals array of I. Great, so that goes to our checksum. Now we need to go and extract the checksum out of the packet, but what we'll do is that this checksum is in binary, and strangely enough, this requires that the checksum is in ASCII here. It's the ASCII equivalent of the hex of the checksum. It's all fully documented here. So if the checksum is added up to here, and there's all the 3H here, the 50 here, etc., all the way to the 20, that will give us a hexadecimal value of 317, and the last 2 digits, 1 and 7, are displayed as ASCII in the checksum. So, how do we do that? It's not too difficult. First of all, let's go and convert our checksum to hex. So we can do this by just formatting into hex with 2 hexadecimal positions, the actual checksum. So that will give us the ASCII equivalent, and all we have to do now is go and check that that equals. So if the first byte of check 0 is actually equal to the packet, and we want the second to last packet, byte a string in packet, so we do length -2, so that's got to be equal, and the second byte has got to be equal as well. Then we know we're good. And actually do an else, because here I'm going to do a logger.debug checksum is good. Else logger.debug checksum is bad. And let's see if that works. Run this. Great, just move this out of the way so we can see what's going on. And we'll actually go and copy play.bin to there. And we should see now that the checksum is good. That's wonderful, because there was the packet, we actually parsed that correctly. And I also have a bad one, just to check. And let's see if what we get from there. And checksum is bad, because we've got a bad packet in. So, our checksum calculation is now correct, so we can safely go and process this packet. So, let's come into here. So the checksum is good. And what we now want to do is go and extract out exactly what in this packet on the status request information back is an MOD, because there's a whole bunch of requests. We can go and get a DSC, which is the type disk in the unit, an SPD, an INF, a whole bunch of things. We'll just look at the mod request. So the MOD is the second, third and fourth byte in the packet. So we will now go and extract the type of the packet, and it's just a substring of 1 starting from, and it's 0 base, that's actually the second byte, and 3 characters long. And then we'll do a switch on the type, and we'll say, okay, if it's a MOD, then we'll call another function called process MOD, and we'll pass it in the stringified packet so that we can process that more easily. Okay, we then need a process MOD. And we'll log into here inside process MOD. Let's see if that works. It's always useful to do a step at a time and make sure that each part works as you would expect it before trying to write the whole driver all in one go. So let's copy that play and see if we get that logger inside process MOD. Yep, we've got inside process packet. There's the packet, checksum's good, and we're now inside the process MOD. Wonderful. Things are looking good. So inside the process MOD, we now need to go and process what's going on, and we'll have another look at that specification. So we've got an MOD packet, and which is here. And this character specifies the transport status, and this parameter specifies the disk format. Just for the purposes of this video, we're just going to look at the transport status, which is 0, 1, 2, 3, 4, 5. The 6th byte, 0 base, that's the 5th one, 5th index, and a 3A here is a play. So we're going to do a switch on packet and the 5th byte, and we're going to say, right, if it's a colon, because we can see here that play is actually a colon, and we'll also catch while we're here a 7, because a 7 is stop, so we'll catch play and stop, and set a break here. So now we're catching the packets, and we know that we've got a status here of play. So what are we going to do here, and how do we get that back up inside StarDraw Control? Well, the answer is that we need to go and store away in a private member variable, let's say the transport status, and we're just going to store this as a string. So we can go and store transport status equals play, and down here transport status equals stop. Okay, and you can imagine that we could have gone through and implemented all the other kinds of transport commands that you can get back. Now we need to expose this private member variable to StarDraw Control, and we can do that by declaring a controllable public property of type string. We call it transport status, and there's just a get, and it returns transport status. Great. Now the other final thing we need to do is actually inform StarDraw Control that it's been updated, and we can do this by declaring a controllable event. So public event, it's of type event handler, and is on transport status changed. Great. So what we'll do here is say, okay, we've got that inside the process mod, transport status has changed, and what we'll do is we'll say if on transport status changed not equal to null on transport status changed, and it takes in two parameters. You just pass in this, which is this class, and an empty event args. That's what you'll always just put these in. Don't even worry about it. And finally, we'll just put a default thing in here. Got a return. So we'll just get out of this, and we won't fire the event if it's not a transport status that we don't recognize. Great. So we are updating the transport status here. We're putting it into a private member variable here. We've exposed it here, and we actually fire an event when that's changed. Great. So let's say OK to that, and OK, and OK. This time we'll come into the UI, and we'll just put in a label here. And what we'll do is we will go and click on this event, and we'll change it to actually be on the serial port, and there is our on transport status change. That's what that event controllable event with event handler did, is it added that menu item there. And what we're going to do is go and set the label, we'll go and set the text property of the label to come from the DVD D01 serial port with transport status. There we go. Now, whenever it receives a transport status command, that label should change. Let's see if this works. Right, so we'll go and copy our play, and it changed. And I've also got a stop. See if that works. And yes, that changes to stop. And just to make sure, change this to bad and make sure that we don't do anything naughty. And we can see in the debugger that the checksum is bad, it fired these events, and everything worked there. Great. So that was a fully bidirectional driver, event driven, creating our own devices, our own properties, our own ports. And you could of course have a request status periodically fire on a timer, so you could add a timer. Let me just do that. I could say if I want this status, I could say let's go and add a timer, and we'll just make this every 1,000 milliseconds, every second. And when we go and click on this, let's go and call the devices DVDU and request status. And so if I actually had this connected, once a second it will go and talk to the device and say, please give me a status. The device will respond sometime later with, this is my status information. We'll update our member variables, fire the event, and you can catch it within StarDraw. The other benefit of doing this is if the device does send out unsolicited messages, for example, if you're using your remote control, say an infrared remote control handheld, and you go and press play, if the device supports the functionality of it sends out this status request or status update anyway, then you will be automatically updated and be in total synchronization with the device. So So that's it in here. We'll also see that there is a, if I come into here, edit this, and edit this, you'll see that that is our full driver. If I select everything here and then copy, cancel, 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 I can then see in my library here, I'll go and edit this, and this was actually our, and there is our driver. But I can go and paste everything into there. So go and update it to be correct. And we've created our driver. And because it's shared, it will actually be uploaded to our server where other people will be able to use your driver if you want to. So again, we can drag it on. So we've written the driver once, and we can have multiple of these devices. And if you actually went into each one of these, you can see it's got your very latest driver. So you can continually reuse the driver in future projects. So just writing the driver once, you can reuse it many times, and you never have to write another line of code to control that device once that driver has been written.